Who's ready for 200 slides of code in 45 minutes? My talk's called 4 Programming Paradigms in 45 Minutes. This is the result of me proposing a talk that I didn't want to give, and then them saying, that sounds awesome, we should do that. So I don't recommend that strategy. I'm Anja Hammerly. I'm on GitHub as Thagomizer. I tweet at @thethagomizer. And I did not include a picture of my cat in this talk, but if y'all ask good questions afterwards, I will tweet out a picture of my really annoying cat who let himself out of the house by opening the door and then got lost for 3 days recently. And I blog at thagomizer.com, and I just released a new blog post on bad managers. So if that's the kind of thing you're interested in, you might go read that. The slides for this talk are also on that domain if you have bad eyesight and can't see the code on the screen, or if you just would rather follow along, on the home version. And I like dinosaurs a lot. So if you're interested, I work for Google Cloud Platform. I'm a developer advocate. So if you're interested in Google Cloud, if you've heard of that thing called the Kubernetes and you don't know what it is and want to chat about it, or if you want answers to questions or opinions about the cloud, I'm happy to share many of those things with you. Come find me in the collaboration room or during breakouts. And since I work at a large company, LawyerCat says any code in this talk is copyright Google and licensed Apache v2. So this talk is about celebrating polyglots. From the outside, programming seems like very prescriptive and systematic and perhaps even boring, but we're all programmers, and we know that there's a lot of variety and creativity in programming. There are many, many ways to solve a problem, and there are many schools of thought or paradigms in the programming world. This talk is about the similarities between languages, concepts like conditionals, collections, assignment, arithmetic. But it's also about the differences. Different programming languages are good for different kinds of problems, and knowing a lot of different kinds of programming language can help you understand the abstractions that underlie everything we do in our day-to-day lives as programmers. When you have these abstractions, you're no longer attached to syntax, and that means that your brain can be more flexible about ways to solve problems, and you can learn new languages more easily. If anything 15 years in the industry has taught me is that I'm going to have to learn a lot more languages over the next 15 years. So in order to show the similarities and differences between languages, I'm going to show the same example in 4 very different languages. And that example is making change. Specifically, I'm going to use each language to calculate how many coins and bills you need to give a customer to make change or to make up a certain amount of money. So with that, let's dive right in. Ruby hack. So we're going to start object-oriented, and of course we're going to use Ruby. And the slides are red because Ruby. Quick overview. Y'all probably all know this, but just to make sure, everything in Ruby is an object. Nil is an object. False is an object. True is an object. Some of you may not know, false and true are actually singleton instances of the true and false class. Objects contain state and behavior. State is like things like fields, attributes, etc., depending on the language. Behavior is what you do with that state, most likely methods. And in Ruby, we refer to the object itself as self, and that's how we modify our own state. For example, self.pet, my cat is named Emma. Objects interact with each other through message passing. If I want to find out the length of an array, I send the length method to a specific instance of the array class. The array object that I sent it to calculates its length and then returns that to me as an integer. When I'm teaching stuff, I usually try to use my own examples because I find most textbook examples really boring. But there's a lot of material I'm going to cover today, and so I'm going to use the canonical examples where I can, so that if you want to go deeper, you have something that you've seen that's familiar when you go to read the textbooks and stuff that I will recommend. And one of the most common examples for OO is the bank account. Basically, let's build a bank account. Objects are instances of classes, so I start by creating the bank account class. Bank accounts need to have a balance associated with them. For a lot of reasons, it's a bad idea to let folks monkey with the balance. So I'm going to make it an instance variable, and I'm going to not have any accessors for it. And I'm going to initialize the balance to 0 when I initialize the object. Side note, I'm representing the balance as an integer number of cents. If you think using floating point for money is a good idea, come find me later, and I will tell you why you are so very, very, very wrong. Floating points are not accurate enough. So throughout this talk, money is always going to be represented as an integer number of cents. So, quick break for IRB. I can instantiate my object. And I know it has a balance of 0 since I just wrote the code, but I can't see that outside the object. So I'm going to add a reader, not an accessor, a reader. to see the balance. Now, I can instantiate the object, and then I can see that its balance is 0. Now we add deposit, which increases the balance, and withdrawal, which decreases the balance. And again, in IRB, I can deposit 100 cents, $1, so withdraw 30 cents, and have a balance of 70 cents. If I was doing this for real, I'd probably add code to prevent overdrafts, add an account number, maybe some other things as needed, build some sort of crazy double entry display for it to make it all look fancy and official, but I've got 3 other paradigms to get through. So I talked about objects as having both data and methods before. In this example, the data is the balance, and it's set and initialized, but also deposit and withdraw all interact with that data. They're all modifying the internal state. My IRB process communicates with them by sending the deposit, withdraw, or balance message, and then the object sends the results back. Strengths of OO. The big one is modeling. The world around us is composed of things, like my clicker, or the seats you're sitting in, or the projectors up there. And it's also composed of ideas, like happiness. And all of those exist in the real world, and we can use objects to model most of those things. And if you have your data and your methods encapsulated together, it's really easy to pick that up and put it elsewhere. So I don't have to write the code for calculating array length every single time I want to have a collection object. A lot of people really like the ease of testing that comes from objects because you can test each object independently, and then you can test the system as a whole once you know that each of the individual pieces are working. So on to the example, making change OO style. So this is the code for my cash register, and you can't actually see that in the back. So let me build it up piece by piece. The class declaration and the initialization. I have an instance variable drawer, which represents my cash drawer. I have 20s, 10s, 5s, 1s, quarters, dimes, nickels, and pennies in the cash drawer. And for all of my examples, I'm going to assume that the cash drawer is sorted because that's how we keep cash drawers. It also makes writing recursive code really easy. So here's the make change method. Make change takes an amount owed and the amount the customer gave you, which I'm calling tender. And then calculate the difference, which is the amount of change I need to give back. And I create a change array, which is where I'm going to store the exact bills that you need to hand over. I'm going to have a variable I, which is the current slot in my cash drawer I'm looking at. And I'm going to have a denomination, which is the amount that is in that place in the cash drawer. I normally wouldn't do this, but it makes code on the slide much easier to understand. So while I still have money to give back to the customer, I'm going to loop through this. Inside the loop, I'm going to see if the difference, the amount I still need to make, is less than the denomination that I'm currently looking at. So if I'm trying to make $7 and I'm currently looking at the tens, I can't use a 10 to make change. And if that's the case, what I'm going to do is I'm going to increment my index and move to the next smallest thing in the drawer. In this case, that would be 1s, because looking at the 5s, or 10s, sorry, 10s, trying to make $7, increment moves me down to the 5s. Yes. And then I'm going to start from the top of the loop again. Now, if I'm trying to make $7 and I'm currently looking at the 5s, I can use that. So I'm going to add that to my change array and then subtract $5 from my difference that I still need to make. Awesome. Simple. It's super easy. So who has experienced with OO before? I should see lots of hands. Please show me hands. So you're probably thinking, that's a horrible example for teaching OO. Aja, why did you do that? And the reason is that, yes, this is a horrible example for teaching OO, but it's much, much, much better example for the other 3 paradigms I'm going to teach you. So let's dive straight into functional programming. I'm going to use Racket. Racket is a general purpose programming language in the Lisp scheme family. Lisp, in turn, is the second oldest programming language. And Racket and Lisp are really well-known, well, Lisp especially, but Racket increasingly is a really well-known functional language and a great way to demonstrate it. And it has lots of parentheses, and I like parentheses. So, functional languages. Who would have thought? They're made up of functions. Functions take in data and output data. I'm going to be doing all my examples in this talk as pure functional. That means I won't ever store or mutate the data at all. As one of my previous coworkers said, mutable state is fundamentally suspicious and cannot be trusted. The nice thing about pure functional style in programming is that the output only depends on the input. There's no state. So if I give the same input to the function every single time, I'm always going to get the same results. Data and procedures are separate in the functional languages. They aren't combined together like they are in OO languages. And I will acknowledge right now, for those of you who are going, that's not true, that I am hand-waving pretty vigorously here. But that is true for the purposes of this talk. So, syntax. Racket uses prefix notation, which is going to look a little weird to some of you. The name of the function is the beginning of the function call. You're probably more used to infix notation. But with prefix notation, if I want to add 3 and 5, I call the plus method with the arguments 3 and 5. The parentheses make it a function call, and I get back 8. And the nice thing about prefix notation is that it's very easy to take an arbitrary number of arguments. So multiplication, multiplying 1, 2, and 3, it's just as easy as multiplying 1 and 2. I can just shove something into the end of the argument list. It gives me 6. The other nice thing I like about prefix notation is it makes the order of operations really clear. Here I'm multiplying 3 and 5, subtracting 10 from 6, and then subtracting 6 from 10, and then adding those together. And I don't have to worry about operator precedence and binding and which binds closer and anything like that. The parentheses and the notation make it very clear what's going on. I can't mess it up. But I said functional languages have functions. So here I define a function by calling the word define and then putting the name of the function in the argument list inside parentheses. And then the body of the function is, in this case, times n because I'm defining square. And then I surround the whole thing in parentheses because yay parentheses. That's just how Lisps work. And then I call the function by parentheses, function name, argument list, 5 in this case, and it returns 25 because that's the square of 5. It gets weirder, don't worry. Conditionals. I'm going to use cond, although there's a lot of other conditional constructs in Racket. Cond is short for conditional, and it acts like Ruby's case statement. So I have cond. It's surrounded by parentheses, because parentheses. And then there's each clause. The first part of each clause is a test. And then there's the stuff you do if the test is true. And if that test isn't true, you go to the next test. And then if the different test is true, you do different stuff. And then there's the else for none of my tests were true, so I'm going to do yet some more stuff. So here's an example, absolute value. First condition, if x is greater than 0, I'm just going to return x. That's the absolute value. If x is equal to 0, I'm going to return 0. Otherwise, I know x is negative, so I'm going to return the negation of x. Simple. Lists or collections, think about them like arrays. Items separated by spaces inside parentheses. You might be thinking, what's with the backtick? Well, if I didn't have the backtick, this would be calling the function 1 on the arguments 2 and 3, which doesn't actually make a lot of sense. So you put the backtick there to know that this is a list literal. I love Lisps. So car gets the first element of the list, or the head, in this case 1. Coulter gets the rest of the list, in this case the list 2, 3. We will come back to car and coulter in just a little bit, and I will explain to you why they have such crazy names. And cons used for making pairs. So in this case I want to add 1 to the list 2, 3. I cons them together and I get the list 1, 2, 3. So quick example, factorial. Define the function fact n. I have a conditional. If n is less than or equal to 1, I return 1, because that's the factorial definition of factorial. Otherwise, I multiply n by the factorial of n minus 1. Simple. Fibonacci. If n is less than or equal to 0, I return 0. If n is equal to 1, I return 1. Otherwise, I add the Fibonacci recursive call of n minus 1 and the Fibonacci call of n minus 2, because that's the mathematical definition of Fibonacci. So strengths. One of the fantastic things about your functional style is that if you don't mutate state, you don't have to have as much concerns when you have concurrency, because you don't have locking tables or shared memory or race conditions or any of that other stuff that causes us problems. I figured out what's going on. It's that mic up there. It's also easier to test. If you only put the same input data and always get the same output data, it's much easier to figure out what you need to test. You don't have to do any setup for setting up state. And it's very easy to see from the code exactly what your cases are. And code that contains no state is safe to reuse anywhere. So reusability is awesome. I like functional programming a lot, and I like it because it's very, very brief. Others hate it for the exact same reason. So making change functional style. You can see, much shorter than the Ruby version. You can actually probably read that in the back. But let's walk through it. Define my function, make change. X is the amount I need to make, and denoms is the denominations that are in my cache drawer. If x is equal to 0, if I don't actually need to make any money, well, I'm going to return a list that is empty because don't give them any bills. Makes sense. If my cache drawer is empty, I can't make change, so I'm going to return false. There's 2 recursive cases. The first one is the case where the amount I'm trying to make is less than the denomination that's at the beginning of my denominations list. So this is the case where I'm trying to make $7 and I'm currently looking at the tens. In that case, I'm just going to call it recursively and use the rest of the stuff in my cache drawer with the same amount. And then the fun case. If the amount I'm trying to make is not less than the denomination I'm currently looking at, so I'm still trying to make $7, but now I'm looking at the 5s, I'm going to take one of those 5s, I'm going to add it to a list that is making the rest of the amount, that's what that minus x car denoms thing is, and my cache drawer. Simple. Don't worry, it gets weirder. We are on to our third paradigm. We're going to do logic and constraint programming. We're going to do it with Prolog. And I promised you I will tell you my favorite Prolog joke at the end of this, but I cannot promise you that it is a good Prolog joke. So Prolog is a logic language used for constraint solving primarily, and it's based on formal logic. And by formal logic, I mean things like all men are mortal, Socrates is a man, therefore Socrates is mortal. And formal logic is at that beautiful intersection of mathematics, computer science, and philosophy, because clearly all of these things are friends and we should all hang out together. Prolog programs are made up of facts and clauses. And the really brain-breaky part of Prolog that gets most people completely confused and wanting to run away is the fact that you never tell Prolog how to solve a program. Prolog figures that out for you. It's actually just searching a possible constraint space. Instead, you have to describe the problem in very explicit detail so that Prolog can then figure out how to solve it itself. So let's say you're solving a logic problem, like, the guy in the blue house has the fish and the guy in the white house really likes to drink Pepsi, like, and trying to figure out where everyone lives and what their pet is and what their favorite drink is. In Prolog, you don't tell it how to do a, depth first search of the search space. Instead, you just carefully enumerate all the rules and constraints and then say, hey, Prolog, can you solve that for me? Which is really, really weird for all of us who've been taught programming using this is how you make a peanut butter sandwich method, because that's not how Prolog works. So the syntax is actually not too bad, but since we don't need a lot of operators, it's not actually that complicated, and it's a little weird. We have variables, which are in all caps, and we have constants, which are in lowercase, and that's pretty much it. I can define facts. Facts end in periods. So I can say that Washington is a state. I can say that Washington and Oregon share a border, and that Washington and Idaho share a border, and that Oregon and California share a border. And then I can say, hey, Prolog, let's make some rules. Rules are a set of what look like facts, but basically what's saying is that x and y are adjacent, x and y are variables, remember capital letters. And then there's that colon minus thing. That's actually a logical implication. Normally I leave that out when I talk about this with people, but every time I've spoken in Salt Lake, the level of background in mathematics and computer science has been really high, so maybe that'll help y'all. That's a logical implication. And what I'm saying here is that two states are adjacent if they share a border, and if the border rule is true. So adjacent is true if everything on the right-hand side is true. And what Prolog does is goes and does some crazy pattern matching. I love pattern matching languages. They make me so happy. And by pattern matching, what it's doing is it's actually doing a process called unification, but that is the only time I will say unification in this talk. If you want to hear more about unification, stay tuned to the end, and I will give you resources where you can learn about that. So Prolog's going to go try to find some values for x and y such that the stuff on the right-hand side is true. So I'm going to say, hey, Prolog, are Washington and Oregon adjacent? Prolog's going to say yes, because that's what Prolog does. It says yes and no primarily. It's fantastic. And then I'm going to say, hey, Prolog, are Oregon and Washington adjacent? And Prolog's going to say no, which, OK, why'd that happen? Well, Prolog is incredibly literal. And I did not tell it that my adjacency rule is reflexive. So if I want to fix that, I have to add a second rule where I say adjacent xy is also true when there's a border fact for y and x, because Prolog. So some basic examples. The classic Prolog example is specifying a family tree. Yay. Here I'm saying that Homer is Bart's father, and Homer is Lisa's father, and Marge is Bart's mother, and Marge is Lisa's mother. And then I can say, hey, Prolog, put the variable in, constant in Bart, who is Bart's mother? And it's going to say, hey, I was able to make that true by saying that x is equal to Marge. I can also say, hey, Prolog, who is Marge the mother of? And it will say, well, Bart. And I can say, hey, you got any others? And that's what that semicolon means, is yes and. And then it'll also say, hey, Lisa, also makes that rule true. Which means I can then define relationships like this. X and y are siblings if there exists some z, such that z is the mother of x and z is the mother of y. And then that crazy slash equals equals syntax is actually not equal, because you're not really your own sibling. That would be weird. So x and y are siblings if there is some z where x is the mother of z and so z is the mother of x and z is the mother of y, and x and y are not the same. X is also y's sibling if there is some z such that z is the father of x, z is the father of y, and x and y are not the same. So then I can say, hey, from our list of rules, hey, Prolog, who are siblings? And it will say Bart and Lisa. Lists. Prolog has lists. Most languages have collections. It's some stuff in square brackets with commas, and they can be mixed type. Looks like Ruby. Yay. But dealing with lists in a pattern matching language gets a little complicated. And Prolog uses this lovely Bart syntax that I adore but confuses people. So this is pronounced F bar R. And F matches the first element of the list, and R matches the rest. This is just like car encoder that I showed you in functional programming. So if I have the list 1, 2, 3, if I pattern match that against F bar R, F is going to be equal to 1, and R is going to be equal to 2, 3. But they're not actually equal, they just match, because equality is not really a thing in Prolog. And the last thing I need to show you is that Ruby, just like Ruby and Racket, underscore is the I'm not using it variable, which I was informed is also pronounced meh. So in Prolog text, you also see this as referred to as the don't care variable. This is the unused argument variable. So member. Member is like include. And if you want to use the pronunciation of include that I learned from my Canadian friends, it's include A from Ruby. So this is member. There's only actually 2 rules. The first is actually a fact. X is a member of something if X is the beginning of a list. Sure, why not? X is also a member of something if there's something I don't care about at the beginning of the list, and X is a member of the rest of the list. OK, sure. So strengths of Prolog. The big thing is the flexibility. So I just showed you member. So I could use that to detect if a number was in a list. But I could also use that to generate all of the lists that contain that number, because you can run Prolog backwards. There's a really great talk using Minicanron, which is another logic/constraint programming language, where they generate all of the Racket programs that will return a result of 120 when given an input of 5, trying to generate factorial. Think about that for a second. They're generating the code by running the program backwards. It's amazing. Prolog is also great for problems that involve constraints. If you've ever tried to do like table planning for a wedding and you're like, well, I can't have these 2 people at the table because they're going to cause problems, trying to figure out how to make everyone work, and the tables only seat this many except this table, which only seats 6 and the rest seat 10 and all that. Prolog is great for that. One of the examples I learned about from doing my research is that there was a research lab where they were trying to schedule use of a shared resource, which I believe was a dolphin. And they were trying to do it around people's class schedules and work schedules and also make sure that they had enough time for the dolphin to rest and they didn't have enough activities on the same page, and they ended up using Prolog for that. So making change in Prolog. Prolog doesn't have return values. I haven't actually hinted at that recently, but it doesn't actually have return values. So you need to encode the return value into your rule. Our change rule has 3 arguments. First is the amount we're making. Second is the coins or bills we have in our drawer. And third is the amount of change to give. Those last 2 are going to be lists. And this is the entirety of the code. It's even shorter than the Racket version. First rule, if I'm trying to make no money, I don't need to actually give you anything back. So I don't care what's in my change drawer. And I'm going to give you the empty list back. OK, sure. Second rule, this is the case where we are not using, this is the case where we are using the amount that's at the current spot in our change drawer. So I'm going to say, we're going to have A, which is the amount. If A is greater than or equal to the first element of our change drawer, F, and B is A minus F, not equality, logical equivalence. There's no assignment happening there in the sense that we think about it. Then we want to make sure that the change we give is going to be the change for the amount B with the same list of denominations, making the list X. So this is really confusing. But the big thing we're doing here is we're doing a recursion. We're taking the amount we need to make still, and we're saying that that amount is going to be made with the bills associated in the list X. And then we're shoving them back in that first line using the bar notation to construct a list instead of deconstruct the list this time. Don't worry, it gets better. And then the last example is the case where we're not using the first thing in the drawer. In this case, we're going to say we have an amount A. We don't care what the first thing in the drawer is. And we're going to say we make that using the list X. If we need to make sure that A is greater than 0, because Prolog will happily go try to make a change for a negative number. And then we do that by calling change recursively on the amount, the rest of my change drawer, and the list of bills we want to make X. So, how many of you are thinking, ow, my brain right now? Yeah. I love Prolog, but even the fact that I love it and it's one of my favorite languages, of all the examples of this talk, including the next one, this was the hardest to write, and this was the only one where I actually had to break into the debugger to make it actually work out and make sure I had all the cases correctly. Because since you're not describing the how, and Prolog is just doing a search of the constraint space, it sometimes does things that you wouldn't think about it doing, because it's just following the rules you gave it. So, on to our last programming language. Our programming paradigm. We're going to do procedural, and because I like hurting brains, we're going to do it in assembly. So, assembly is old school programming. Actually, I was talking to some folks at RubyConf about this, and they described assembly as a memory shell game. And yes, assembly is in fact a memory shell game. There's a limited vocabulary / number of functions standard lib. I'm going to be using the assembly from the book NAND to Tetris, which I think is the elements of computing systems or the fundamentals of computing systems. Lots of assemblies exist. I'm using this one because it looks the most like ALGOL languages, which is what we're most familiar with. If you know assemblies, you're going to say that's not an assembly. Yes, I understand it is not a traditional assembly, but it's easy to understand and it still has all of the joys and love and problems of an assembly. So syntax, I'm working with registers. The arithmetic logic unit I'm using has 2 registers, A and D. D is the data register. It just stores data. And circling back, car and cdr from the racket section. Car stands for the contents of the A register, and cdr stands for the contents of the D register, which is why they have those really strange names. So the A register is multi-purpose. It can store data, like the D register, but it can also store memory address. In that case, it accesses locations in memory. To make this slightly easier for us, we're going to use M to represent the A register when we're using it to access memory. Follow? Okay. So I can do some basic computations. I have A plus D. I can do D minus A minus D. I can do A or D increment plus 1. I can do a decrement. I have not and or bitwise operators, and I have negation. And then I have increment by 1, and I actually have decrement as well by 1. Just a note, I don't have multiplication, division, exponentiation, any of those things that we just assume that we have mod. I have addition, subtraction, increment, and decrement, and some bitwise stuff. And yet, I can still do really cool things. This assembly allows for assignment, and it looks like normal assignment. We can assign to any of the registers or to memory, and we can do that in different ways. We can assign when we're also using the variable. So I can say D equals the result of D minus A, and that's just fine. And I can also assign to multiple locations at once, which is super weird and super handy when you're doing crazy assembly things. I can load an integer into memory with this syntax. So this will load 100 into the A register, not into memory, into the A register. And I can use this syntax to load in the line that the program counter needs to move to for this particular label in the code. And this lets me do jumps, which are the only form of control flow I have. So goto lives again. And I have a limited number of jumps. The format for jumps in this language is you have a value, a semicolon, and then a jump type. All of the jump types are with respect to 0. So JGT is jump if the value is greater than 0. In this case, I'll be checking to see if the value in the D register is greater than 0. I have jump equal to. This is going to always jump, and I use this for unconditional loops, similar to our whiles. I have jump greater than 0, jump less than 0, jump greater than or equal to 0, and here are some basic examples. Add. I added some registers because it helped me understand what was going on better. So I load the constant 2 into the A register. Then I put the value in the A register into the D register. And then I load the constant 3 into the A register. And then I put the value of D plus A back into the D register. And then I load the constant 0 into the A register and store the value in D in the memory location referred to by the value it's in the A register, which is 0. Got it? Here's summation. Lots of code here, but we'll do it piece by piece. So I load the value 0 into the A register. I store the value that's in the A register into the memory location that I'm referring to with the address in the A register, which ends up storing a 0 into memory location 0. Because, let's do 2 things at once with the value. I then load the constant 5 into the A register, assign that to the D register, and then load the constant 1 into the A register, and then assign the value that's in memory that's in D to the memory location referred to by the address in the A register. What I'm going to be doing in this example is summing up the numbers 1 through 5. I declare a loop. This is a label that I will come back to. Then I load the value 1 into the A register, assign the value that's in memory location 1 to the D register, load the constant 0 into the A register, and assign the value of memory plus D into memory location 0. So we now end up with 0 in the A register and 5s everywhere else. Then I load a constant 1 into the A register, and I decrement the value that's in memory location 1. So now D and M are both equal to 4. And then I have a label end, and I'm going to jump if the value of my D register is less than or equal to 0. Otherwise, I'm going to jump to the end. Otherwise, I'm going to load up my loop label from earlier, and I'm going to jump unconditionally back to the top. So now I'm back at the top where my loop label is. I'm going to load the value 1 into the A register. I'm going to copy the value in memory 1 into D. So now D has 4. I'm going to load the constant 0 into the A register. And then I'm going to increase the value that is in memory location 0 by the amount in D, which is going to make it 9. And then I do the decrement again, and then I loop back to the top, and I add 3, and so, and so, and so. And then eventually, I will get the sum of 5 to 1. Awesome. So, strengths. I don't have any problems that assembly currently solves for me. I've written the assembler for this particular assembly, and then wrote the bytecode that creates the assembly that the assembler reads, and then I wrote the high-level language that creates the bytecode that creates the assembly that the assembler reads and turns into machine instructions. But I did that because I wanted to know how my wizard box worked. Procedural style, though, can be really useful. It's simple. For us, most of our first programs were procedural. Hello World is very procedural. Most scripting is procedural. Do a thing, then do this other thing, and then do this final thing, and then clean up after yourself. And procedural style is really easy to write. We think about the world in sets of instructions. It's very easy for us to explain things as a list of things to do in a specific order. So here's making change in assembly. I am doing this the stupid way. There are better ways to do this. We can talk about that after my talk if you're interested. And this makes the change, calculates the number of coins you need to give out and what coins you need to give out to make change for 67 cents. So the first memory location holds the amount to make. Memories 1 through 4 hold my coin denominations. Memory 1 is 25 for quarters. Memory 2 is 10 for dimes. Memory 3 is 5 for nickels. And memory 4 is 1 for pennies. Memories 5 through 8 hold the number of each coin to use. Memory 5 is the number of quarters, and so on. My assembly doesn't actually let me refer to memories by number that way, but it does let me refer to them as registered, so that's what you'll actually see in the code. So this bit here loads a constant 67, the amount we want to make, into A, then moves that to D, then loads the address of register 0 and puts the amount in D into that location. So now we've got the amount we want to make in memory location 0. This loads in the values, 25, 10, 5, and 1, into the appropriate memory locations. And this is the actual code. And I'm not going to do the magical table of registers here, but I'll walk you through it. So I load the location of my first memory location. I then assign to D whatever value is there. That's the amount I still need to make. I then load up the value of memory location 1. And I subtract the value of memory location 1 from the amount I need to make and store that back into register D, or into register D. And now I load up the label for my dimes code, which is the next thing I'm going to go to. So if D is less than 0, which means that the amount I was trying to make was less than the value of 1 quarter, well, I don't need any quarters, so I'm just going to jump to dimes and start trying to figure out how many dimes I need. But if it's greater than 0, I'm going to load up my memory location 0, store the amount I have left after I subtract out 1 quarter's worth into that location, and then I'm going to store up the location of where I'm keeping track of how many quarters I need. I'm going to increment that by 1. Then I'm going to load up the address for my quarters loop and go back to the top and see if I can put any more quarters in. Awesome, huh? And then I do the same thing for dimes, nickels, and pennies, and eventually you end up getting the right answer. So learn more. I covered a lot of material in this talk, and I didn't go into any depth on any of it. I really encourage you, if you're interested by any of this, to go out, learn more, and seek more. If you want more resources on functional stuff, There's a talk, parenthetically speaking, by Jim Weirich from Golden Gate Ruby Conference in 2010. It's on Confreaks, and it is really, really good. It got me to actually go back and work through the entirety of the structure and interpretation of computer programs with a bunch of friends. There's also Functional Principles for O Development by Jessica Kerr from Ruby Midwest in 2013. And Why Not? The Adventures in Functional Programming, which was a keynote given by Jim at RubyConf 2012 in Denver. And I like functional programming, and I followed up until about the halfway point. And then I got lost. So I've gone back and watched the video a couple times, because when you watch the video, you can stop and think, and like, okay, what is Jim showing me there? But he eventually builds up the Y Combinator in Ruby, and it's awesome. If you're more of a books person, the Little Schemer, the Reason Schemer, and the Season Schemer are fantastic. They're some of my favorite computer books because they're written in Socratic dialogue, because why not? They also use food as all the examples, and they're pretty easy to work through. I've given them to newbies to code, and they've gotten through just fine. And then there's the classic Structure and Interpretation Computer Programs, the Wizard book. It's only got 5 chapters. How bad can it be? It's really intense. It is all you need to know about computer science. You end up building an interpreter. You also end up building a constraint-solving system in Scheme, and it's fantastic. So you like logic programming. I gave a talk at Cascadia Ruby 2012 called A Taste of Prolog, which just covers Prolog and tries to use magical color coding and animation to make it make slightly more sense. You can go watch that on Confreaks. My favorite Prolog books, there's The Art of Prolog, and there's Prolog Programming for Artificial Intelligence, but the one I like the best is Cause and Effect, Prolog Programming for the Working Programmer. We are working programmers. This is our book. The reason I like this is it has exercises, because it's really easy when you're reading a nerd book to like, oh yeah, it totally makes sense, and then you realize that you haven't actually retained the stuff in a way that you can use it. So having exercises means you have to sit and try to work through stuff and then look and see if you got it right. Procedural code. The book I mentioned that assembly came from is The Elements of Computing Systems, Building a Modern Computer from First Principles. Oh my gosh, I love this book. You start with the NAND gate. You build up all the logic gates, and then you build up memory, and then you build up an ALU, and then you build up an assembly and a machine code that works with that ALU, and then you build the assembler, and then you build a byte code that generates that assembly, that generates the machine code that uses the ALU that you built out of the NAND gates and the other logic gates that you build up. And eventually you end up writing a language called Jack, which kind of looks like a really stripped down version of Java, and then you can write Tetris and run it on your simulated circuits that you made. It's awesome. It's really, really well done. There's actually a Coursera course for it. I worked through it before there was a Coursera course. But if you don't know how your wizard box works, I highly recommend it. I managed to get through my CS degree only vaguely understanding architectures and operating systems. And this really helped a lot. And it also helped with PLs, programming languages. So I did a bunch of programming languages. Y'all can probably, oh yeah, 7 languages, 7 weeks. Yeah, it's a book. There's good things, bad things about it. I'm not 100% fond of how they did Prolog, and I don't think it focuses as much on the similarities, because not implementing the same thing in all the languages makes it very hard for you to see what languages are good and not good at. Someone else turned me on to the exercising programming style, which is like 50 styles/paradigms, all implemented in Python, all solving the same problem. And it's awesome. So I highly recommend you try that. I'm still working through it in Ruby. Because Python's fine, but I like Ruby. So I'm supposed to do a thoughtful closing right now. Yeah. Hi. Polyglots are awesome. The big thing I want folks to take away from this talk is that knowing lots of languages, having these concepts abstracted in your head is good. And if you are helping folks become better programmers, or if you're trying to become a better programmer yourself, get out of your comfort zone. Don't just use high-level object-oriented languages all the time. Having an appreciation for the other ways of solving problems can help you pick the right tool for the job. I will point out that the making change solution in Prolog was actually the shortest solution there. If I was going to solve something logic-based, I would definitely use Prolog. If I was going to solve something where recursion seemed like the right solution, I'd probably actually fall back to Racket. I wouldn't go to Ruby. Eventually, I might do some IoT stuff where I want to use assembly, but I use procedural style all the time. So knowing your tools well and knowing what tools are good for particular jobs will make you a better programmer. It will make your code better, faster, and easier to maintain. And also, get out of your comfort zone. Don't just let yourself become stale. There's going to be new languages all the time. My current language of the year that I'm going to try to learn is Elixir, because someone told me it's both functional and pattern matching, and I was like, I'm there. I don't know what I'm going to use it for yet, but it seems super cool. So it might be the next big thing. I know a bunch of folks who got really interested in Go a couple years ago, and now Go is the thing. I don't have problems Go solves, but a lot of people seem to. So learn new languages, get better at stuff. I have stickers of many, many dinosaurs in my little pouch over there. I want to say thank you, and I think I have time for one question. Questions? Yeah. Yes. Oh, I was going to tell you guys my Prolog joke. How many Prolog programmers does it take to change a light bulb? No. You can also do yes, but I like the no version better. One more question? You have one right there?
That was my question.
Yeah. Prolog's actually a full language. It's surprising how little you need to be Turing complete. Someone has proved that you can build stuff in Minecraft that's Turing complete. So Turing completeness is interesting, but not sufficient to be usable in my experience. Well, thank you all. I'm very glad to have spoken here.